Okay then, so here's our lesson on the gas laws. Okay, but first of all we're going to deal with the ideal gas equation. And what I'd like you to consider is we have this piston, or a cylinder, and there is a piston that's attached, and this piston can go back and forth, back and forth, back and forth. And inside we have a certain volume, and also we have a certain pressure. Now, if I was to push that piston in further, and let's imagine it reduces the volume of the cylinder, then the pressure is going to increase. Why is the pressure going to increase? Well, you can imagine these particles that are bouncing around inside will have a smaller volume to bounce into, and so therefore they more frequent collisions with the wall. And pressure is merely the particles bouncing off of the walls and imparting some momentum. Okay, how does this relationship look mathematically? Well, if as the pressure increases, the volume decreases in an inverse relationship. Fantastic. Let's just rearrange that slightly. PV is going to equal a constant. And this is what we know as Boyles Law. Okay, there we go. Now, let me give you an example of how this is going to happen. Okay, let's take an example of a fish underwater. Here's the fish, and there's the seabed. The pressure at the surface of the water is 1 times 10 to the 5 pascals. That's the pressure at sea level, and the fish is running at 6 times 10 to the 5 pascal pressure. In actual fact, he's about 50 meters deep. Okay, let's imagine the fish farts. The small bubble is going to come up to the surface and expand as it goes. If we know that the bubble is 30 centimeters cubed initially, what's going to be the volume at the surface? Okay, let's use that equation before and let's try and work that out. Okay, so what is the volume of the fish fart at the surface? Okay, we can make use of this equation before very simply. We can say to ourselves that the pressure and the volume at depth must be the same as the pressure and the volume at the surface. We're looking for the final volume, so if we rearrange the equation, we get P1 V1 divided by P2, which gives us, let's substitute in the values. 1 obviously means deeper, 2 means at the surface higher, so we have 6 times 10 to the 5 by 30, and that gives us a volume of 180 centimeters cubed. Now, we could have converted into meters cubed and worked it through, but as long as we're consistent from one side to the other, we should be okay. Let's just remind ourselves of how to convert, just in case we have to convert in one way or the other. We need to bear in mind that 100 centimeters is the same as 1 meter. So therefore 100 squared centimeters is the same as 1 squared meter. We also need to bear in mind that 100 cubic centimeters is the same as 1 meter cubed. And so this is going to be 10 to the 6 centimeters cubed. Bear that in mind. That's an important relationship to hold in your minds. Okay, so there's the first example. Let's deal with the second example. Let's deal with Felix and his balloon. His jump from space. Yeah, I'm sure you've seen the video, and if not, then you can look at it on YouTube. But his balloon looked very, very small initially at the surface. However, when he went up into space, it suddenly took the shape which is much more familiar to you as the balloon, because it's increased in volume. Why is it increased in volume? So this is an edge of space. Well, because you know that as you go higher into the atmosphere, the pressure decreases. If the pressure is decreasing, then the volume must increase, according to Boyles' law. Okay, then let's put some values onto this. At the surface, the volume is going to be 10 to the 5 meters cubed. It's rather big. The pressure at the surface is 10 to the 5 pascals. And I've suggested the pressure at the top of the atmosphere, right at the edge of space, is 1 times 10 to the 4 pascals. It's actually likely to be very small, but however, let's just try this anyway. What is the volume going to be? Here's new volume, let's say. Well, let's look again at the relationship we have. P1, V1 is equal to a constant, or indeed it's going to be equal to P2, V2. So it doesn't matter whether you first of all worked out what the constant is and then substitute the values in, or you could just bypass that stage altogether. So let's just, I think it would be quicker to bypass that stage, and we're all competent enough to know the maths of having to work out the constant. 10 to the 5 by 10 to the 5, nice and easy figures, divided by 10 to the 4, and that gives rise to a volume of 10 to the 6 meters cubed. So it's much more increased. It's got much larger. Okay, we can come back to this page later if we need it. Superb. Of course. Now, the next thing we need to consider is that this balloon, of course, has changed other considerations as well as it's gone high into the atmosphere. As it's gone high into the atmosphere, of course, there is a change in temperature. And how is that going to start affecting the pressure and the volume? And so that leads us on to our second law. If this first law was called Boyles' law, then the second law we need to look at is how temperature affects the pressure. So let's go back to the cylinder. And we are going to now imagine that plunger stays in a fixed position. So we have a volume, but this remains fixed. We have a temperature, and we have a pressure. Now, as we increase the speed of these particles, i.e. the temperature, and they're moving around with a greater speed, so they're going to be able to make more collisions, more frequent collisions with the wall, and also they're travelling at a higher speed, so they're going to impart more momentum as they strike the wall. So therefore, as the temperature increases, hopefully you'll appreciate that the pressure increases. So how does that make a difference? Well, what's the relationship to that? Well, if we have the pressure is going to be proportional to the temperature, or the pressure divided by the temperature equals a constant. And this is known as Charles' law. Okay, then you might have seen this for year 10 already, because it gives rise to a really, really useful graph. This is a graph which you'll be plotting yourselves. And it says that if we plot let me just draw it up here, it's a side, the pressure against the temperature in degrees Celsius and the pressure in pascals, then our plot will look very much like this. If we track back that line, we will see it intercepts the temperature axis at approximately minus 273 degrees Celsius. In other words, this point is absolute 0 Kelvin, suggesting there that when the particles stop moving, they're not going to exert any pressure at all. So once again, we're going to start doing the same maths as before. We know that pressure divided by temperature is equal to a constant. But remember, we kept there the volume the same. We also know that the pressure times the volume equals a constant, and there we kept the temperature the same. I've just drawn this line, it just makes life a little easier. Don't worry too much about it because we're going to put it all together in our next step, and therefore our next step suggests that you can vary all three. Pressure times volume divided by temperature equals a constant. And this is Charles's law. Okay, let's look back at those examples that we had, the fish farting in Felix and his balloon. Here we go, let's take a look at the fish to start with. Let's put a temperature variation into it now and see what we can get on. See how we can get on. There's our fish. There's the bubble. And we know that the pressure down here is 6 times 10 to the 5 pascals. The pressure on the surface was normal atmospheric pressure. We were working on a 30 centimetre cubic bubble that drifted up to the surface, and my calculations previously gave rise to suggesting that it was 180 centimetres cubed the bubble was when it got to the top. So this is the first volume, temperature, pressure. However, the new information we're going to be told is that the temperature down here is at 7 degrees Celsius, whereas the temperature on the surface is 21 degrees Celsius. So what's likely to take place is that actually the bubble is going to get even bigger. So we want to find out that new volume. Why is it going to get even bigger? Well, it's because we have a proportionality with temperature. If the temperature increases, then therefore the pressure and volume multiplied must be bigger. Okay, let's try and work out what it's going to be. We can say, as we did before, P1V equals a constant, and then those initial conditions will be the same as the final conditions. So let me say that we are looking for the new volume, V2. We have P1 V1 over T1 multiplied by T2. Let's move T2 up, and I want to get rid of P2 there. When I substitute the values in, P1 is going to be, so we have 6 times 10 to the 5 multiplied by 30. Remember, it doesn't matter, as long as we're consistent, we can keep that in centimetres cubed. Divide that by our temperature of initial temperature is 7 degrees. However, what we mustn't forget here is that that must be in Kelvin. In other words, this here must be in Kelvin. We have a pressure at the bottom here, which is 1 times 10 to the 5, and of course the temperature at the top is 27 plus 273. Nice even numbers there. And that gives rise to 189 centimetres cubed. Slightly bigger. Not considerably bigger, but that's because the ratio of these temperatures in Kelvin is very small in the difference. So therefore we get a slight increase from there to there. Okay. Let's go back to Felix balloon and let's try and have a guess at what's going on with him, with the temperature consideration as well. Okay, back to Felix's balloon. On the surface, it's very small. And we said the pressure at the surface was atmospheric pressure, 1 times 10 to the 5 pascals. The volume was conveniently the same, meters cubed. And the temperature on the surface, we're going to call it 17 degrees. Now, up in space, let's imagine this is the answer to the first question, where we didn't consider a change in temperature. But if and the values were, the pressure up here was 1 times 10 to the 4 pascals. we said the volume is 10 to the 6 meters cubed. It's very large, because we thought the temperature was 17 degrees Celsius. However, this is not the case. In actual fact, I'm going to suggest the temperature is running at minus 10 degrees Celsius. And so therefore, I'd say the balloon is slightly smaller. Smaller temperature, it's exerting less pressure. Substituting in all the same values, of course, because the pressure is about the same, what is the new volume going to be? Well, let's just go about exactly as we tried before. P1 V1 over T1, P2 V2 over T2. This is my second volume, this is my second pressure, this is my second temperature. This is my first, and first. We're looking for V2. P1 V1 over T1 by T2 over P2. And that gives us 10 to the 5 by 10 to the 5 by 273. So it's minus 10 degrees Celsius, which converts that to Kelvin. My new pressure at the top of the atmosphere. And obviously my original temperature at 17 degrees. And that gives me 9.07 times 10 to the 5 meters cubed. So actually we're right, we've slightly decreased from that value because the temperature is actually lower. Okay then, right, let me give you an attempt, a question to attempt. We're going to try we have a bottle, a 2-litre Coke bottle, which obviously we have our volume at 2 litres. The pressure is going to be 10 to the 5, and the temperature is going to be 17 degrees Celsius. We then have the first situation in which it starts to be heated and the heat goes up to 87 degrees Celsius. It's slightly expanded to 2.2 litres of volume. Now what I want to know is what's the new pressure in that situation. And then thirdly, we are going to heat it until it explodes. And I'm just trying to think, I need to give you another value for this. I've just forgotten the value for the temperature. Let's imagine an exploding pressure is going to be running at, what should we call it? Let's say it holds quite a lot. Let's say it holds 5 times the atmospheric pressure, and it can't exceed the volume of 2.5 litres. So at what temperature does this thing explode? Okay, give it a go and let me know what the answer is.